Now this lecture is going to be a bit different. I'm going to show you also other functions that you can use to fit your models, but it will be mostly about one technique, bootstrapping, that is very easy to use with programming and very hard to use without programming. And this is very useful also. So I wanted to dedicate a lecture to this because when you're dealing with processing data, knowing that this exists and having an idea of how to do it can be very helpful. So the general idea here is that bootstrapping is a resampling method that allows you to simulate the whatever analysis you're doing with what would happen if you had a different data set. So we're going to look at first an example, a simple example, comparing lung capacity or forced expiration volume when the volume of the lungs that you can expel when you really try to. And then I'm going to also talk about residual bootstrapping with enzyme kinetics. So these are different, slightly different techniques. They apply to different situations, but the basic idea is the same. Okay, so let's start with this comparison between the FEV. So this is what the volume you get when you force the expiration of the air from your lungs, and the correlation with height. We have this data set. This is a data set on children. Some of them were already smokers, most of them were not, but we're going to look at sex and height and the volume of the lungs. So basically, we're going to read this data and using pandas and then select the different categories. So we start by importing NumPy and pandas. We're going to read the data. This is the FEV CSV file that we have here. And now I'm going to separate into two tables. So all those rows where the sex column is equal to male, I put in the male table, and the rows where the sex column is equal to female, I put in the female table. So this way we can separate our subjects according to sex. And now we can use pandas to plot the distribution of height and lung capacity for the two different tables. But one tricky thing here is that if you use a plot from a data frame, it will automatically create a new figure by default. So if you want to put the two plots in the same figure, you need to get the axis either by just creating the first figure and then getting the current axis from pyplot. I forgot here. You need also this, otherwise this would not work. So we can get the current axis and give it as an additional argument to the plot methods in our data frame. So if you do that, instead of creating a new figure, it will use the same figure, the same axis, and this way you can put both plots into the same figure even though they come from different data frames. So we're going to plot on the x-axis the height column, on the y-axis the expiration volume, and we're going to use a scatter plot. We're going to, I'll be here, so follow the usual convention of blue and pink. So this is a bit stereotypical, but it's easier to understand. I'm going to plot the male subjects blue and the female pink, and we have the chart here. So we see that there is an obvious correlation between height and lung capacity. So this is evident. Larger subjects tend to have larger lungs. But one thing that we can ask is whether there is some difference in the patterns here that we are not quite seeing in this distribution. So are these groups any different? we're going to test this by fitting a polynomial curve of degree 2, which I'm not choosing for any particularly intelligent reason. This is just an example an excuse to show you how to do a polynomial fit. So we're going to use a quadratic curve to adjust this, because this seems to be slightly curved, so maybe a quadratic curve adjusts better, but I have no physiological justification for this curve. So let's assume this model where the lung capacity, so the volume you can exhale as a function of your height, is some parameter multiplied by the square of your height plus another parameter multiplied by your height and an additional parameter here. And now we want to find these parameters. So we're going to fit this data to a second degree polynomial. This is easy to do. We have this from the NumPy library here that we imported. We have this Polyfit function. So this does a least mean squares fit. It minimizes the quadratic error of the predictions and the target. And you put in your x values. You put in the desired y values. So the x values will be the height of the individuals. The desired y values will be the lung capacity of the individuals. And you give the degree of the polynomial. And the output is the set of these three parameters. So the coefficient for the square, the coefficient for the x, and the independent one as an array, an NumPy array, that best fits the polynomial of these x values to this target. So you can do this with any degree. So if you do it with higher degrees, you get more parameters here. But we're going to do both for degree 2. And now we're going to create a figure, plot the data like we did before, and also create here 100 points spread out between the smallest and largest value of the height. So this is basically the set of points on the x-axis we're going to use to draw these curves. And now we're going to compute the curve for the male subjects, and this is simply the evaluation of this polynomial, the male curve 1, given these values of x, so we can draw the curve. So we can do this easily with Polyval. Polyval is compatible with Polyfit because it assumes the parameters in the same order. First the one with the highest exponent, then the second one, and so on. So we're going to draw the male and female curves, again using the stereotypical colors, and we can see a difference here. So the curve for the male subjects is clearly curved like this, so it starts increasing faster, whereas for the female subjects is nearly a straight line. So is there a difference between the two data sets? Because just by looking at the best fit, we have no idea of what the confidence intervals are for these parameters. Maybe this just happened because of the way the points are, but this is so uncertain that it could have been easily the other way around or something like that. So how could we tell if this difference is significant or not? There are probably sophisticated statistical methods for this, which I didn't look up, but we're going to use bootstrapping, which is a sort of a one-size-fits-all solution for these kind of problems, even when the model may be very complex. So suppose that we could find another set of subjects and repeat this experiment. So we would get another set of points, male and female. We would fit the two lines, and if they differed a lot from this one, and we would repeat and repeat and repeat, and if sometimes the male line would be straight and the female one curved and vice versa, then we could reach the conclusion that this was just by chance. It's not an actual difference between the groups. It's just happened that the sample we had was like that, but if we had another sample, it would be different. Unfortunately, in general, you cannot do this. You have one sample and that's it. You cannot just repeat the experiment all over again or get new data and so on. But we could create a replica of the data with the same probability distribution. And the way we can do that is to resample from the data we have and create a replica that is a random set of values from the data we have. So we do sampling with reposition. It means that we can select individual examples repeatedly, but we do it randomly from our data set. So in general, each replica that we create will have 2/3 of the original data, but then some of them will come out repeated, so we have the same number of data points, but with some repetitions. And each replica we create will be different from all the other replicas because they have different combinations of examples there. However, the distribution of values will always follow the same distribution as the original data because we are randomly sampling from the original data. So this is the generic recipe for bootstrapping. You create replicas of your data by sampling with reposition from the original data and creating replicas of the same size. They will not have the same points because some points will be duplicated and others will be missing, but you have replicas of the same size and the same distribution of values. And now we can use those replicas to try to get statistics on the parameters of our model. So let's see an example here. We start with the X and Y values, so these will be height and lung capacity. We also specify the number of replicas that we want and the degree of the polynomials we want to fit. And now we start with an empty list to store the parameters we get for each replica. And for all the replicas we want, note that we don't really care about which replica, what the index of each replica is, but we want to do this as many times as is specified here. For example, 500 times. So for each of the replicas, we're going to create a random array of integers that goes from 0 to the length of our data, so how many data points we have, and has as many values as the data we have. So for example, suppose that you have 100 data points. This will go from 0 to 99 and will give you 100 values from 0 to 99. So if we use that as the index of the values we're going to copy from our data, we get a random sample from our data with some repetitions and some missing values, but it's one of those replicas that we create by bootstrapping. And this is very easy to do with Python and with programming in general. You get random indexes and you extract from the X values and the Y values the same examples. Note that I'm using the same indexes here because I need to match the X to the Y values, the height to the lung capacity. And now I'm going to do the polynomial fit with the replica that I created. So this is not the original data, this is a resampling of the data. And this will give me slightly different values for the parameters. So these 3 parameters that I computed here will change with each replica because each replica is a different set of points sampled from my original data. So I'm going to append the parameters here, and in the end I'll return an array with the list of parameters. So this is a matrix. Since the degree is 2, this will have 3 columns, one for x squared, one for x, and one for the independent value there, the constant. And I'm going to do that for the male subjects. I'm going to do this bootstrapping for using the height and lung capacity of the male subjects, and the same thing for the female subjects. Now there is one small detail here. When I did the Polyfit back here, I didn't care about using the pandas series, because if you send your pandas series to some operation with NumPy where the values will be used, then the series also works. The problem is with indexing, because pandas series have those special indexes, and if we want to do something like this with the pandas series, it may not work quite as we want. So in this case, I'm sending just the values, so just the NumPy array for the height and weight, so that these indexes are the actual positions and not the indexes of the series. But this is just a detail. Just remember, if you are unsure of whether or not to use series or NumPy arrays, or you need to use NumPy arrays, if you are unsure, just put the values there after the series and use the NumPy array without the indexing of the series. Okay, so we have male and female matrices of parameters. So for each of these, we have 500 rows. And for each row, we have the 3 parameters for x squared, x, and a constant computed using a different replica. And now we can look at the distribution of these values to see if there is an actual difference between the two groups. For example, let's look at the first one, the parameter for x squared. We want to do a kernel density estimation graph with the parameter of the first with the distribution of the first parameter. And an easy way to do this is to take the first column of that matrix, turn it into a series with panda series, and then just call plot KDE on that one. So you can use kernel density estimation from SciPy or scikit-learn or something like that, or if you're using pandas, you can just convert it into a series and plot. Note that I don't even care about this series, so I'm not keeping this series in any variable. I'm just using it to do the plot in a convenient way. So the same trick, create the figure, get the axis, and do both plots in the same axis. And this way you can compare the distribution of the first parameter for female subjects and male subjects. So it's easy to see that they hardly intersect. So at least on the quadratic term here, so basically what is giving the curve this shape, there is an actual difference between the two groups. When you do resampling and you recreate these data samples, you get a distribution of values for this parameter, but it's not wide enough to overlap the two. So we can say that the groups are different in this respect, and we can see the same thing for the parameter 1, so the inclination of the line, and for the last one, the constant there. So we can see that they are actually really different, the shape of the points when we consider male and female subjects, comparing the relation between height and lung capacity, which probably makes sense because as children grow, they start becoming different, especially in the upper torso and the skeleton and so forth. But this is a way of testing whether or not those differences were statistically significant by using bootstrapping, which is very simple to implement. Okay, now let's see a different example, which is residual bootstrapping. With bootstrapping, what we saw is that we took a random sample of our original sample. So when we do this here, we are selecting a random set of subjects with some repetitions. But sometimes this does not make sense because it may be that you have sampled the data at some fixed points. For example, suppose you're following some time series or some process over time, and you measure your data every 5 minutes. It makes no sense to resample from that data and get 2 copies of the data at minute 25 and no data at minute 30, because you would never do the experiment like that. So for these cases where simple resampling is not adequate, what we can do is we can assume that the errors between the prediction, between our best model and the data, those are the ones that are random noise. So basically, we're going to compute the parameters for the model, the best parameters, and we're going to compute the predictions for each of our data points. So each data point will have some difference from the predicted value, some error. So this error is the residual for that data point. We can assume that these residuals occurred because of some kind of random noise. The data point is not exactly where predicted because some random things are also affecting the data. And now we can resample these residuals, these errors, and generate replicas by shuffling the residuals between different points. So I'm going to try to illustrate this with an example. Suppose that we are doing this kind of enzyme kinetics work where basically we measure for a set concentration of substrate that we choose. we measure the velocity of the reaction at the beginning. So when the enzyme starts converting the substrate, eventually substrate starts to disappear and the reaction slows down, but we measure the initial reaction, which is the velocity at which the enzyme is converting the substrate. And we know that as we increase the concentration of the substrate, if we follow this Michaelis-Menten kinetics, we are going to start having this curve that will saturate to some, it will tend towards a maximum velocity as we increase the concentration of the substrate, and will approximate that maximum velocity asymptotically. Now we can do we can compute the model, something like this. So we have, for different values of substrate, we registered the initial velocity, and now we compute this curve that will tend towards the maximum velocity at infinity, and also at this point where we reach the half point towards the maximum velocity, we have this additional parameter, the Km, which is a concentration of substrate that gives us half the maximum velocity. So we have this data. These are the concentrations of substrate that we chose to test. These are the velocities that we measured, and it doesn't make sense to sample randomly from here because we actually chose these values. These are not random values. We chose to do the experiment with this concentration and this concentration and so on to get this spread of data points. So what we're going to do is to start with this first model. So basically, if we don't use programming or computers, we can linearize this equation and do a least mean squares regression to a straight line. But it's best to actually adjust, fit the model explicitly to the data that we have. So the first thing we're going to do is to find the parameters here. So the two parameters are the maximum velocity and the Km. We're going to adjust these so that the curve fits as best as possible our data. To do this, we just need to write a cost function that we're going to minimize. So I'm going to use minimize from SciPy, and we're going to start by creating this cost function. This is just a quadratic error between the curve described by this equation and the actual measurement of the initial velocity we have here. So our function is going to receive the parameters we are trying to optimize, and these are the Vmax and Km, which are the parameters for the equation. And it's also going to receive the substrate concentration and the measured velocity that we have in our data. So these two are the actual data, and these two are the Vmax and Km parameters. And our function is going to compute the predicted velocities by using the first parameter, which is Vmax multiplied by the substrate here. So this substrate is an array with all these experimental values. And so when we do this product, we also get an array of the product between this scalar and this vector. And the same thing here. So this is the other parameter summed to the substrate concentrations. And this gives us the predictions for all the velocities that we should have measured. And now we're going to compare these predictions to the actual measurements and sum the squares of all these differences. So this is the quadratic error between what we predict for a given pair of Vmax and Km values, the quadratic error between our predictions and the actual measured velocities. And this will be the cost that we're going to minimize, or the error that we're going to minimize. So remember, you should always test your functions. I'm going to skip that so that we have time to reach the end here. And now we're going to compute the values of Vmax and Km that minimize this cost, so that minimize the difference, the quadratic error between the predictions and the experimental data. We're going to get from SciPy optimize this minimize function, and this minimize function is actually very powerful. There are lots of other things you can do with this, including second derivatives and so on. So I'm just going to show you a simplified version of using this. But we get the data. The data is a matrix like this. The substrate in the first row and measured velocity in the second one. So we're going to put this, the first row is the S, the V is the second one. And now we're going to call minimize, so that minimize will minimize the output of this cost function. So this is what I'm putting here. We're going to give an initial guess of 1 for Vmax and 1 for Km. These are the initial parameters. But this vector also tells minimize how many variables we're trying to adjust. So how many parameters we're trying to adjust. And then there are these extra arguments that we're going to send to our function. So what we put here in the arguments is just sent to the other function, similar to what we saw with oddInt a while ago. But here we also have this additional argument that we can give, which is constraints on the bounds for our parameters. So for each of these parameters, we can tell the lower and the upper limit. In this case, I don't want them to be below 0 because it doesn't make sense to have negative values in these parameters. I don't care about the upper limit, so I set 0, none on both of them. There are other things that you can do with the minimize function. You should look up the documentation if you're going to use this, but this is just a basic way of using it. And what this minimize will do is to call the cost function with different combinations of parameters and find where there is a combination that reaches a local minimum. And now it returns this object, which has lots of information about how many iterations it did, what was the final error, and so on. But we only want the X attribute, which gives us the optimal values of the parameters that are being adjusted. So this would be the Vmax and the Km, and we have here the optimal values. So this is the way we can do, we can fit our model using the minimize function. And now we can just plot everything. So we have the Vmax and Km that we got from the optimization, the original data and the file to save the figure. So we just create an x-axis. This is the same trick using linspace. So we have a nice a set of 200 points so we can draw the curve smoothly. And now we compute the predicted Ipson values, which is for each of these x, Vmax times the x divided by Km plus the x. And now we create a figure. We draw the red line with our model, and then we put we draw the markers, the crosses with the data. So basically we have this plot here where we show the prediction from our model and the actual data. And we also can print out the Vmax and Km. So Vmax is 73 something that we got here. So at the limit it will reach that velocity, and this is the Km, the concentration of substrate that reaches half of Vmax. But now the thing is that what is the confidence interval that we have for these values, because this is just the best curve we have here, but we can see that there is quite some margin the data has around the curve, and the curve could be slightly above, slightly below, and we would like to have an idea of what is the confidence interval for these parameters. So this is where we can do residual bootstrapping. In this case, we won't do bootstrapping because it makes no sense to omit some of these data points and to have some of them repeated, because these were carefully chosen on the concentrations of substrate. But these residual errors here are random. This point fell above the line, but it could have gotten that error and could have fallen here instead of above. The same thing for any of the others. So we can estimate that if we repeated the experiment, we would have something approximately like this, but with different residual errors for our points. So that's what we're going to do. We're going to shuffle, resample with reposition those residual errors and generate replicas by putting the residuals at the same spots in the concentration that we chose, but giving different errors relative to the original curve. So we get different data sets, different replicas by doing this. Now, for each one of these replicas, we can compute the best curve. And the best curve will be slightly different because the errors were shuffled in a different way, the points are in different positions, and we get slightly different curves. So this is what we're going to do here. This is the residual bootstrapping function that gets the Vmax and Km for the best model. So this after we adjust our model, so actually the best hypothesis, but the best Vmax and Km we found. The data that we have, the original data, so we can compute the residuals, and the number of replicas we want. So we start by creating the prediction curve from the parameters and using the substrate concentrations in our data. So basically what we are doing here is computing these points here that fall on the same x values of our data points. So we compute each of the points in the best curve that we have that correspond to the data points. And now we compute the residuals. The residuals are this predicted curve, the difference between the predicted curve and the original data. So all those errors, sometimes the data falls above the curve and it's positive, sometimes below and the residual is negative. And now we do the same thing. We start with an empty list for the parameters. We loop through all the replicas. Actually, this could be like this because we don't care about that value. And now we're going to get a random sample or resampling of our residuals. This is a set of integers from 0 to how many columns we have in our data. That is how many data points we have. And also we want as many as the data points that we have. So now we're going to create a replica by adding to our best model here the residuals selected at random with this roll of the dice. So this is why residual bootstrapping is different from regular bootstrapping. We are not selecting the data points, we are selecting the errors between the data points and the best fit, and then using those errors, shuffling them, not exactly shuffling, but selecting with reposition. It means that some of them can come up repeated, and we are going to use that to create a replica. Now we're going to call the minimization function to get the best Vmax and Km parameters for this replica, and we're going to append that to our list. So now we're going to get a matrix with all the Vmax values on the first column and the Km on the second column. We can get the mean value, so this is very close to the best model that we have, the best parameters that we found initially, but we can also get the standard deviation. So this is something that is very hard to find without bootstrapping, because now we have an idea of how spread out our estimate is because of the way the data fits more or less, or our model fits more or less the data. And we can also look at the different curves. For example, here I plotted all the different lines with some transparency, so we can see where they get denser and how spread out they are. And also you can do kernel density estimation or histograms, whatever you want, with all the parameters you found. But basically the important thing here is that with just about a dozen lines of code, you can go from just having the best parameters you found to having a good idea of how your parameter values are distributed and what the uncertainty is for this distribution. So this is what you get with bootstrapping and residual bootstrapping. Depending on the kind of problem, you may need to use one or the other. And it's very easy to implement with a bit of programming, and gives you a lot more information than what you can usually get with a spreadsheet or some other way of processing your data. Okay, to sum up, bootstrapping is not an easy thing to do if you need to do it by hand, because if you need to do 500 replicas, even if you do it on the spreadsheet, you need to copy the same thing 500 times and so on. And with a bit of programming, it's very hard to implement because you just generate replicas and repeat the same processing for each of the replica. Residual bootstrapping is a variant where it doesn't make sense to actually resample the data, but you can resample the residual errors with respect to your best fit. So this also gives you an idea of what could have happened if the data had different random errors. Okay, so this week, unfortunately, I could not update the PDF file because of all the evaluations in the other courses. I'm going to try to do it in the next few days. But for homework, I have the description there. You have the zip file with the data. And what I want you to do is the same thing we did here for the lung capacity with respect to height, using these different sets and the curves, but I want you to separate the subjects between smoker and non-smoker. Regardless of sex, we just segregate between smoker and non-smoker and see if we can find a difference that is significant. So what would be a significant difference would be something like this, where the parameters hardly intercept. But if you have one curve overlapping the other, then this may be just because of the spread of the data, and you cannot have much confidence that the curves are actually different. So this is what I want you to do for homework this week, is to, based on this lecture, just adapt the code to do the same thing for smokers and non-smokers instead of male and female. So this should be trivial to do because most of the code is done here in the slides, and you can just follow the lecture and do it for the different groups. Okay, so for this week, we are now entering the late stage of this course where I'm not focusing so much on Python and the basics. We covered that in the beginning. But mostly I'm starting to focus on specific things that you can do with programming that go beyond what you could do without programming. And for the next week, I'm going to cover machine learning. So I'm going to talk a bit about regression, classification, and clustering. We're going to use scikit-learn, which is a very powerful machine learning library that you can use with Python. This will just be a brief introduction to machine learning, but will give you the starting point for using these tools. In the meantime, for this week and the next, I will not have so many exercises. Of course, if you still have questions about the previous part of the subject matter, you could review the exercises. But for the plan for these tutorials this week and next week is to get you started on your final project. So we start going away from these basic exercises, and each of you will have their own questions about what you want to do with Python and specific applications. So we should dedicate some time this week and especially next week to that kind of problems. In order to do that, if you have something left behind that you didn't understand very well, then go back to those other exercises and try to keep up so that you can start applying this to something that actually interests you and not just doing the exercises. Okay, so that's it for today. At 7 o'clock I'll start the Zoom meeting, and if anyone wants to talk or ask questions, we can talk a bit. Okay, see you soon.